and then
But
it will be easier.
we should not insult anybody, right? Yes.
Yeah, the recording is still already on progress, and then I'll meet now. Yeah, again, yeah, I'll be away from my computer. Please call me if you need to restart the Zoom, okay?
Okay.
All right, thank you.
Of course. Thank you, Daka.
Cool. What are you gonna do once you guys? That's I was going to
That's the other one. That's okay.
What's the first time?
We should put it after.
But it's the same on the walls.
Yeah, but you have a new max with it.
A new layout,
Huh?
a new resolution thing, or new layout.
Also, both.
Okay. I didn't saw it.
No, it's not online. You have to ask it for. I have it. That's why it's.
Do you have to speak the right question?
Yeah.
Hello, everyone. Thank you for coming for the seminar. So today it's my pleasure to introduce you Dr. Flavia Rommel. She has a bachelor's in physics from the Federal University of Southern Frontier, Brazil, a master in physics and astronomy from the Federal University of Technology of Paraná, also Brazil, and a doctorate in astronomy from the National Observatory, Brazil. She has been working with stellar occultation predictions, observations, and data analysis since 2016. She was on the team that discovered the ring systems around the dwarf planets Rommel and Flavia, and recently published the first topography characterization using only stellar occultation data. So,
Thank you, Carol. Hey guys, it's visual. And I choose a topic which is more or less a summary of the most impressive pursuits that we as a collaboration did so far. So I will place through many different things, including the topics that I just mentioned. Well, my presentation has four parts. The first one, I will show you what are the objects that we are interested in, and define what is a stellar occultation for those that either saw one or heard about, and mention the results, the most impressive results that we have, and what are a few expectations, some of the expectations that we have for the future. So starting by the objects, we are interested mainly on Centaurs and TNOs. This picture is a little, this animation is a little bit old, but you can see here the orbits of the giant planets in Zion. And you can see a lot of dots orbiting the sun in this region. The Centaurs are represented by the orange triangles, and the TNOs are these points outside, mostly outside the Neptune orbit. So this is the location of the objects that we are interested in. So remember that Earth is really here inside the giant planets. It's really far from us and hard to obtain data of these distant objects. The motivation. So due to the distance that these objects has from the sun, they obtain information from the epoch of the first solar system formation. So we are interested to derive physical parameters from them and try to improve our theories about solar system formation nebula and how it evolved until we get the current orbits that we know. Yeah, so we can basically define physical parameters using stellar occultation. Depends on the amount of data. And this is a really nice plot that shows how we evolved since the first stellar occultation we detected in 2009, and then how the Gaia stellar catalog helped us getting more reports. And nowadays we are getting more or less 70, dozens of stellar applications per year, but not all are from Centaurs and Centaurs. So there are another objects. My talk will be about Centaurs and Centaurs. So this number probably will increase a lot when SST discover more objects, so we can predict more events and observe the most interesting ones. So it's an increasing data set that we have in hands, and it should increase even more in the future. But what is a stellar occultation at all? A stellar occultation happens when the fake body faces in front of a star. I don't care about the star at all, so whatever star is good for me, but I need to know when this object is blocking the stellar flux. And when this happens, a shadow is projected over the Earth's surface, and we can mobilize people to observe this star and see the event. And depending on the position of the observer, it will be different data sets. The observer located in A and E observe this event, it will not see the star blinking due to the asteroid facing front of it, because they are outside the shadow. You can see the shadow here, and A and E is outside the shadow. Otherwise, the B, C, and D observers will see the star blinking because of the asteroid is facing in front of it. And this way we can rebuild the shape of the asteroid at this moment. So it may be a little confusing right now. I hope it became clear later. But what you need to know right now is that depending on the location of the telescope, you will see or not see the event. And when you see on your data the event, we call this data positive. I'm defining this because I will use this word later. And when we don't see the star blinking, it's because it's a negative data set. Okay? For instance, A and E are negatives. Okay? How we know when a stellar occultation happens? Basically, what we need is an accurate position of the asteroid in time and an accurate position of the stars. That's why Gaia helped us a lot, because Gaia has an high accuracy in positions of the stars. And now we are working hard to get accurate positions of the asteroid. And then putting both together, we can identify events when the asteroid faces in front of the star. And then we organize campaigns and everything to get them. Okay, so we know when it happens because of this. We propagate the order and we predict the events. And once we identify a stellar occultation by a given asteroid, in my case, Centaur or TNO, we build these stellar occultation maps. This is not a good one, okay? Just for comparison with Nixon. But usually they're better. You can see here the Earth surface, the night part of the Earth, the predicted shadow path, and the errors. It's very large intentionally. We will show another one next slide. And usually when it's these large error bars, we don't make campaigns at all. We just try to get smaller error bars before making campaigns. But we make a lot of these plots and we try to identify the best ones to make the campaigns, mobilize people. Then when we identify a really good one, based on the magnitude of the star, on the region that the shadow is facing and everything, then we contact these people, ask them to observe, and if they observe, they send us the images trans. Okay, so this is a quick summary of how things work. And if we don't have another way to get better position for the asteroids like this one, this is a really large area. So we need to get it smaller. And one way to do this is in performing classical astrometry, which is basically observe the asteroid and try to get positions better. to update the ephemeris, update the prediction, and then maybe have it from here. And usually when we are able to do this, we can observe at least one image. I mean, at least one observer can take data, and then we can improve to a much better prediction, which has smaller error bars. Still not ideal, but better than the first one. So this is how the process works. We are doing this all the time for many objects, and sometimes we got very special good events, bright stars, and in a populated region, so we can get a lot of data in only one night, which is an example that I will show you today. This is the second object, okay? So this is the older prediction, this is the new prediction after only one detection in star occultation. So it's really a creative data. We can do a lot using 1, 2 data sets that observers take. But how the data looks like? They are not that beautiful pictures colored that we saw on the internet, okay? So just to give you an example how our data looks like, I do this video. This is the star. And it's that. So it's not a cloud, because we have another stars here that are not running. They are not blinking. Yeah.
I suppose this video is accelerated.
Yeah.
So how long takes an occultation? 30 seconds from you?
Yeah, it depends, because it depends on the size of the object that's blocking the flux of the stars. It depends on the velocity of the shadow is moving over the surface. And that varies a bit, but usually not more than 10, 15 seconds.
Wow.
So it's really, really quick. You must be prepared in the right time, otherwise you will lost forever. So you have one shot. And another thing in this video, despite the main blink, there are another blinks on it. I just replay again so you can try to see it. Then the main blink, down back, and another blink. You saw that?
Yeah.
Okay, so this was new at the time. This is an application by a ring system. I will specify more later, but this opening basically a new work in our work. Yes.
So, I know since, but, and maybe you'll talk more on this later, but how do you distinguish like those things from random gas or other objects?
Yeah, I can say it now, because we are using photometric methods to measure the flux of the star, the flux of the background star, and comparison stars. So this is a really, really small part of the sky. It was an atmospheric thing, all stars will be affected by it. So using comparison stars, we know that it's not an atmospheric thing. And actually, this was the first detection. We detected these rings again and again, many times now. So we using comparison photometry, we can just put out this possibility.
About how many arc seconds is the size of that? You know?
These images exactly, I don't remember, but I images from the Danish telescope in Chile.
Okay.
So probably it's not that large. I don't remember exactly numbers.
Yeah. So it's probably a pretty small.
Yeah.
field of-
Yeah, probably they are using some configuration for crop image also, because we need fast images. Yeah. Usually we have I think larger field with more stars, usually. This one is very small. Okay, this is simulation. I mean, you can imagine that you are on this, I don't know, space station, and you're looking the event happening back on Earth. The same event that I showed you the video. So if we could do this, you will see the shadow placing over the observatories. So it's just an imagination thing. And you can see here red dots. which are the observatories that participated in this campaign and that observed the event by the main body. Okay. Blue dots are observatories that were able to detect only the rings. Okay. So when you put all these data, use a negative, okay, detected anything else. When we put all this data together in this pipeline, we have, and for that, this is an example of how a light curve looks for the main body, and the two short links before the event and after the main that you just saw in the video. And this is an example of how it looks like the data of the blue dots that only detected the rings. Okay. When we put all together in this pipeline, we can rebuild the profile of the object and measure its diameter, its shape at this instant, and also measure the thickness of the rings and how separated they are each other, because these days are two rings. So you can see here the numbers from the original paper, 7 kilometers in resolution. So this is how accurate the technique allows us to do science. And remember, this is a center, so it is orbiting to the sun between the giant planets. It's not too close to us. Okay. Well, I think I demonstrated the capabilities of the technique. When we put this information coming from stellar rotations together with photometry, which means measuring the flux variations due to asteroid rotation, we get these rotational light curves. Putting all together, we can constrain the 3D shape of the body. Not exactly, but we can constrain a lot. We can also say more or less how is the density if we assume that is an equilibrium shape object, so we can make some calculations of what density it can have and what it could be the composition. So we can start to construct these things using both techniques together. So this is our final range for many objects. There are not many that have this information. Rotation information is really hard to get because usually they have magnitude 19, which is really hard to get with the smaller telescopes. So usually we have rotation data, but not rotational data. So we need to run together big data in rotation to get these kind of results. Okay, so questions.
So back on the slide, was wondering about the ring. So you talked about the constraints of the body here, and wondering about the ring.
Yeah.
Do we know? So are you placing? Is the data giving you a constraint on how small it has to be? Sorry, on like the minimum size it has to be to see the observations we see, or is it? Or do we have like a true, like can we use the available data to say, well, it's this diameter, so we know it's, like, so we know the true size?
Okay,
Exactly.
good question. Good question. When we have only one rotation, it's hard to say the 3D shape because we have an instantaneous picture of the object. So we don't know if it's like a populated asteroid and we just take one picture, we don't know how it is using only occultation. So it's a bit hard. But when you start to get the same object in many rotations, you will see the diameter varies. So you can get rotational light curves also together. And if they have high peaks like this one, we can say that is not spherical. So you can put all together and start to say it can be an asteroid or it can be an ellipsoid. And you kind of need to put everything together. Only occultation is not enough to say it's spherical or it's oblate in 3D dimensions. The
That's about the
answers.
size of the ring.
Oh, the ring.
Yes,
Um,
so like if you go back to slide, 12, or,
this one.
you know, 2 more.
This one.
11, sorry, 11.
Okay.
So you see how you have the blue lines, I assume are the size of the ring? So,
Yeah. Yeah.
and
This
then you have a negative and the yellow, so we know it can't be that large because,
Yeah. Exactly.
but we didn't get an observation on the edge of the ring. Like we only got an observation, like close to the edge, but not the edge. So is
Not
this like,
here, for instance. Maybe.
right? So, could it be possible that the ring is a little bit larger, or do we know that this is the size?
Use this example in specific. Probably not, because when we put all this data, all the light curves that we have with these detections on the sky plan, it looks like this. So it must be a circular ring or a elliptical ring. So we fit using mathematical methods, we fit using all the points, and then if we just go here and come back. So to have an okay, I cannot say exactly the point,
Sure.
but probably is not that large in this direction. But in this case, we have many points. If we have only 2, 3 points, then this constraint is harder because of the number of 3 parameters that we have in the fitting. To fit an ellipse, we need at least 5 points. So if we have only 2, for instance, imagine that we have only these 3. So it's harder to constrain. Depends on the number of points that we have.
Does your fit to the rings, like jumping off that question, does your fit to the kind of the shape of the shadow ring, and kind of thinking that the rings are actually circular, does it help you understand, or I guess see the direction of the pole of the spin axis pole orientation of the object itself, like better? Does the fit the ring and its probably direction help you see spin direction?
You need to make some assumptions,
Yeah.
but yeah, it helps.
Yeah.
It helps. Because usually, as far as I know, usually it should be more or less in the equator of the body.
Yeah.
So yeah, if you know more or less the plane of the ring, you can assume the direction of the plane.
Very good.
More questions? Well, this chariot was the first one detected, and it was in the paper is from 2014, and it has 250 kilometers. So it's bigger Centaur, but the smaller one here in this picture. After that, we get only one ring, not a ring around Flavia, which is at TNO, so it's farther away from us than Chariot, and it's bigger. And you can see on the comparison period. And Haumea is also very interesting because it rotates really, really quick. One rotation is completed every 3.9 hours. So it's a fast rotator. Big object. It has 2 moons also. And as far as I remember, a really red spot in the sun. So it's a kind of combination, weird things. It's really fun, and it was a big finding here. And last year, we found 2 rings around another big object. It's also a TNO, and this object is a dwarf planet candidate. And the difference between these findings and the other ones is that these rings looks that are not homogeneous. So they vary in quantity of material. Sometimes the detection are deeper, sometimes they are shallow. And also they are much farther from the main body than the other ones, as you can see here. And this breaks the theoretical limit of the Roche limit, proposed by Roche. So this limit is the theoretical limit where rings can be formed from the center of their main object. And they are outside this limit. So now it's quite shaking the dynamic people because it's not expected and we cannot explain exactly why they are there and why they still there. And well, this is the situation for power as far as I know right now. So about rings, these two discoveries, and about ring-like features, there is Chiron, which is also a centaur like Chariclo. And Chiron was discovered a long time ago. It was already classified as comets, then centaurs, so it's a kind of weird mixed classification. And he has cometary behavior sometimes. Tails were detected. Activity registered recently. So also it's a very interesting object. And a paper also published last year is showing that this object has a disk around it, and inside the disk of particles there is ring-like concentrations, which are represented here by these ellipses, power ellipses. So it's being interesting. I mean, we have a collection of 4 very interesting objects right now, and when we discovered Chariclo rings, we thought maybe this is a single case, I don't know, we need to investigate more. And now we keep finding more interesting things, and maybe rings in small objects are very common, and maybe we are just starting to discover them. And again, these structures are really, really small structures, so we cannot see them in this using even space telescopes. It's really hard to go. And the occultation are revealing these interesting structures. Yes. Question about rings? Not yet. Another interesting feature that we have been detected, and this was the first one in 2017 paper, is topography. The only TNO that have topography, some topography information is Pluto and the satellite count, and both because of new horizons. But we detected in this light curve something in the surface of this object, which is actually a Earth. The resolution of this light curve is not that good. We have one image in every 3 seconds. So we have only 5 points here. It's not that good as this one, for instance. But we see that we were expecting this kind of sharp occultation thing. And we are seeing intermediary points here. I'm not expecting this one, but it should be like this. It is not. Why? So the paper is really dense, if you want to take a look. But the authors discussed these points and proposed 2 theories for this kind of light curve and not even sharp edge. And before I'm saying the theories, this light curve is located really, really in the edge of the body. So kind of almost miss it, the rotation. So it's really tangent, like a grazing event. And so they started doing a global fit, like the Chariclo, to determine the object size. And then they studied this point in specific. So the plots are mirrored. So the point in A here is the first image. And according to the paper, is an image that started before the rotation. During the exposure, the object blocked the star, and then we have 1.5 seconds of star blocked, 1.5 seconds star not blocked. That's why we have an intermediate point. And they keep discussing how these another points appeared. There are the chasm solution, which is only one topographic and deeper thing. And there is another possibility of having like depression on the moon, and then keeps blinking many times during one exposure, during one image. So it's really interesting how they work with this unique light. Then after this event, we keep going with stellar occultation. We never saw this again until 2020, when we started to look for occultations for this subject. Yes.
Good question. Regarding the last slide, when these shadows are transmitted from the starlight onto the Earth, are you limited? And if you were to do this topographical, are you limited by the fraction of the light coming from the universe? I guess this can be about how precise you're able to get and topographic based on the shadow diffraction.
Yeah, the present diffraction is considered here in this analysis, so we are not very this. But each image covers many kilometers here, and the present diffraction is only 1.2 kilometers, the effect. So it's, I mean, the light curves are dominated by the exposure, not by the diffraction. And the star is also kind of very small. So yeah, this one is. This object is special to me because I made my thesis on it, so I really like it. It is also a TNO, one of the biggest ones, but since they discovered, it's not big, but since they discovered it here, it is facing in front of the galactic. So right now it is here, but it is a really dense and crowded field. So it was really hard to obtain any astrometry, I mean, get the position of the object among the remaining stars in the image. So this is an image that I subtracted to try to subtract stars. These are stars. You can see the object moving. But there is so many stars near here that usually get merged with stars, and we cannot measure the position or the photometry or whatever. We don't have rotational vector for this one, for instance. So it was not good in that sense, but it was good for stellar occultations because in part more stars, right? So we started on trying to get this object on 2019 with this stellar occultation specific. And I think they were on other attempts, but this one we get it. And on July 9, we got 2 parts, 2 positives, and here is an example that Tyler asked about the limitations, a negative here. So if you see the position of the other here, you have one positive here, the negative here, and another positive here. So we don't have 5 points to plot the ellipse, but we have 4 points, and we have a negative that we know for sure that the shadow was not facing here. So we can do the fit and just exclude solutions that are going to be eliminated in the self-direction. This was the prediction lines, and here we got the event. So it was very close.
You say the yellow when you talk about it, you call it positive or also
positive? Sorry, I changed the color because there are plenty of presentations together.
So the top right yellow.
Yeah, positives in yellow here and negatives in blue.
Because she said that was they almost catch the it was past a little bit upper than they were.
Yeah, this was the prediction. We predicted it was facing here, but actually it faced a little bit on the right. And the error bars were really, really large. As you can see. The event could happen since here until here, and it happened like here. It was really close, even though it's a really hard object to measure. So once we got this occultation, we got another 9 cellular occultations for this object because we were able to derive a center here which is very accurate, so we can predict the next one there. And this one is the event that we got more data since we started quarantine looking. So the colors here are the same than before. Yellow are positives. The lines are the prediction. So you can see here the uncertainty is much smaller than before because of that first detection. White dots are people that were bad weather, technical problems, blah, blah. In blue are negatives. Okay, there's some more here. I think so. That's very some. So putting all this data together was really hard. I took many months, but in the end, when I projected everything on the sky, then it worked. This is the picture. It's amazing. It's the best TNO picture that we have. And we didn't detect for sure nothing in this region, but we can see here in blue the link of the object with a really high resolution, and in red are the densities of each data set. And we were expecting, because of the size of the TNO, we were expecting something in hydrostatic equilibrium. So in soil, in spheroid, we're expecting that. But looking at this picture, what do you think? It looks like round, shaped object. You can see something that it's not expecting. To me, it's clear, of course.
Looks like a trunk you're taking.
Any, no?
I mean, does it look, to me, it kind of looks like a spinning tire, like similar to, not quite like the, I don't know if you're asking me this.
Yeah, it depends as to what the point you're thinking. I mean,
It sounded like you were asking us
what it looks like. Yeah,
Yeah, like a spinning top almost. To me.
okay. Yeah, I think to me that I work with this, it is thing here. It's like someone picked a bit on it. And this was not expected. We were expecting something similar. And if you look here, it's kind of square thing, then it gets shorter here. So I didn't sleep many nights because of this. Okay? I was checking everything. I was checking the data, I was checking the spectrometry, I checked all these data sets again and again. And this thing does not disappear. So it means that could be viewed. And at that point, I started to investigate what it can be and how we can determine what is it. And after many months of work, I got a model for this topography. So what the data are saying to me is that it's a crater-like depression here, about 320 kilometers large, and a kind of mountain here, a bit smaller, which can be the rim of the crater or not. I'm not saying that, but it can be. And maybe we are not seeing this ring on this side because we don't have enough data on this region. So this is really, really interesting because in the case I showed before, it was only one data set showing topography. In this case, we are seeing tens of data sets showing topography. So it's the first time that I have data to do things like this, to model the topography of a large object like this thing. So it's really exciting because we are measuring topography miles and miles away from the object. Yeah, it's really fun. I didn't call it crater in the paper because it's the first time that we detected this kind of topography, and it can be depression only. We don't know. We don't have this instantaneous picture. If we rotate the object, we don't know if it's still there in the crater or not. So I use it the word depression, but it can be a crater. Thinking in this direction, I try to explore a little bit more this theory of the crater. For instance, we have another large craters in the solar system. I don't know if you are familiar with Vesta, which is the main belt. Yeah. It has a really large crater on the South Pole. It's not in the hydroscopic equilibrium, but it's rated corresponds about 88% of the median diameter of the object. So it's really, really large. This is, as far as I know, the most impressive crater in the solar system. Following Vesta, there is another large craters like this one in Thetis, which is a Saturnian satellite. And that has a crater that corresponds to 42% of its median diameter, which is this one, because it's Odysseus. So it's also a large crater. It's also already identified, measured in the solar system. And the crater I find, possible crater, I find in MS4, it's also 40% in size. So it's possible to be a crater. We have another examples of large craters. And there is another satellite minus that also has a crater. So kind of looks like that it can be a crater that was identified in MS4. That is really, really interesting. Because looking and Carroll papers, the size of the craters the people find there are 10 to 15% in size. So which is the most, if it's a crater, it's the most impressive one in the TNO region. So it's really cool. Another numbers here, main belt asteroids between the sizes usually have 45% diameter ratios for the craters also. So it's not, this far is not that far in this range. As I mentioned, the Thetis and Mimas also have this range of craters on the surface. So as far as the same range. Another point that comes out when we think that this feature is a crater is about the collision of families that we know. For those that are not familiar with the collision of families meaning, there are some families in the main belt asteroid that many bodies came from one body. So the main body was break up, and nowadays there are plenty of bodies, and you can track back and know that they came from the same main body. So that's the idea. In the trans-Neptunian region, we know that Haumea has a collision family, but it's the only one that we know. So if it's a crater, maybe MS4 also have a collision family, so maybe we should take a look on it. Because if it throws it an impact, it is really large. Another thing that we can think about is the absence. We only know one collision of family in the TNO region. This absence is an observational bias, or this region was less, there were less frequent collisions in this region during the solar system formation. So answering these questions will help us trying to figure out what happened when solar system was evolving. future perspectives. I put here SST because it's the large survey that we are expecting to have data soon. And it will discover a lot of TNOs. Currently, we know about 3,000 TNOs, more or less. It is expected that when SST finish the first 2 years, we will have more or less 40,000. So it will be a lot of objects to predict observations for sure to observe. The astrometry, I mean, the positions measured by SST will have decent accuracy for the painting objects, and it will be really accurate for the brighter ones. So we probably don't need to spend too much time looking for the object to update the depth of the shadow anymore. Probably, I hope. So let's see. And also, after a few years of the survey, we should be able to get colors and photometry and absolute magnitudes of these objects, which also help with the combined analysis that I showed you. Right now, these are my expectations about SST. Another point is the space missions. We already get some quotations from space also. So this is an example published in 2022, where Kelp's mission was passing through the shadow in the right instant of this occultation. So, of course, was lucky, but we got data from land in Australia, and also from Kelps when Kelps was here. So it's becoming real, the possibility of getting stellar occultation from space, and then not having the problem of atmospheric effects that we have here in Earth. And so we are starting this also. James Webb also observed one, but the paper is not published yet, so we need to wait a bit. And the expectation is to get more. We are working to predict stellar occultation to be observed by Kelps, by James Webb. It's more difficult because the orbit of the Neptunes keep changing, you know, keep changing, so we cannot predict too much in advance, usually a few months. This makes things a bit complicated, but it can be done. Yeah. Okay. Questions?
Let's see. Any questions for the audience online? The room, please.
So on the last slide, that space telescope for that mission, did it shadow anywhere on Earth that would have been able to see the application into it?
I'm not sure I understood.
Um,
This one?
yeah, so the mission on the screen, did
Yeah.
that cast a shadow on Earth, or I guess I'm even not understanding the
Okay.
geometry there, but
I will try to explain it to you. Yeah. This is the shadow that I was showing you since the beginning. Okay. It wasn't observed here. Normal, nothing new. And Kelps was orbiting in this direction. Okay. She was placing here. So when the instant that the occultation happened, the instant of the object facing of the star, it was here. In this green point. So when it was facing here, it just turned into the direction of the star and catching. Probably
like it was so like it was to the side of Earth.
Yeah,
the
it's not-
object, and then
yeah.
it thought of it.
yeah, because it faces through. It's like start out of the earth, the shadow, and then it comes every point here, it's 1 minute. So the shadow is here, and it's here, and it's here, or it's facing. So you can plan when the Kelps is facing here and see if you cross each other.
I thought it was interesting when talking about the diameters of these small bodies and the size of the craters. that they all kind of statistically cluster. Is that because when the colliding objects get bigger, they just don't survive?
Yeah, they do.
Okay.
I mean, I don't know much about colliding things. I'm not a specialist on that, but I needed to research a lot because of the thesis and this possibility of being a crater. And this was the larger examples that I find,
Yeah.
So right now, yeah, but who knows?
Seeing the crater on MS4 is super cool. Since finding the internal composition of thin noses is really hard, I guess. Some of that is very challenging. If you have an impact that might expose surface below, the upper surface would be using the perspective, you think it would be interesting to try to see if there is a change in the surface composition when it's for and crater. You think it's possible? You think it's worth it? Can we do it?
I don't know, spectra is not my thing. Carol, what do you think about doing
I
spectra?
think if we knew the rotational period, we could take a shot and try to take like resolve in time spectra to see like different parts of resolve the different parts of the object, but since we don't know the rotational period, it would be like impossible.
Yeah, it's
Just
hard,
the-
We don't know the rotation of the no, it's cool.
because it is facing in front of the galactic plane. So it's really hard to measure. This was an attempt to get rotational data. As you can see here, the shadows of many stars. So there are, I think it's 10 images only that I put here to complete this image. But I got data from 3 nights in this attempt. And I got, I think, 20 points. It's really, really hard because when it became closer to these fainting stars that are not appearing here, I get contamination from the star. So it's really hard to obtain 100%.
It does have a like they don't rest in spectrum, right? Some of the reasons.
Yes, but we have one spec and we don't know like from which part it is, but if you keep kind of observing each year, taking one spectrum and then compare them over 5 years, 6 years and see if they look the same, if they look different.
You could use an instrument that observes simultaneously in different filters. And you do the electric photometry because it's exactly at the same time you may detect some variation. But in an instrument that is observing simultaneously and also you need to be very patient to go the second meeting back.
Very big.
Actually, that it needs to look that bad. It's usually
Yeah, this is
bad
the-
for
the best one.
I've seen worse. I usually can't see anything.
Could you please go back to 2003 easy before? Occultation?
This one?
Yes, this one, the previous. Yes, this one. I was wondering because from, I don't know how many presentations of occultation I saw, like, and I heard that when they don't have this box shape, it could be some kind of local atmosphere.
Yes.
the bird. So in that case, the two bottom latitudes, they don't have this box shape.
This one?
Those two, yes. So in which way you discarded the possibility, they discarded in the paper the possibility of a local or very thin or some kind of activity in its body.
Okay. Before like saying on the paper, these line curves have higher resolution data. You can see that the points are sparse than this one with that one. This is one thing that should be considered. And usually when this shape the low resolution line curve is hard to say that it's something. You need a high resolution line curve to say, oh, it's a ring, it's nothing super. So this is a
One of
point.
the limitations.
Yeah, I read the paper, not this week, but I didn't saw mention atmospheric things here, so we don't use exactly on this paper. these light curves are also located more or less here. So they're not that crazy. Could have, but it's hard to say because of the resolution.
And in the case of MS4, some of the light curves has this shape too, like different from a box.
Yeah.
And how will you describe it? I like
Well-
atmospheres, but I would like to see
Yeah, I don't like
some.
it.
I like it.
Yeah, I mean, the high resolution curves I have on this floor has also a thing like this one,
Mhm.
and is located here. Is this one.
Mhm.
So this very tiny light curve is very accurate and also have a topography detection. I didn't put here
Mhm.
because it will become long presentation. But the noise is also high. So I could say, oh, okay, it's not a topography, it's an atmospheric thing, but the noise is high, and the probability of being a topography, in my opinion, is higher than having atmospheric thing. So there is another paper, I don't remember if people mentioned this, I remember the discussion on this on Vada, remember? That they are discussing more about atmosphere, if you want to take a look. And there is Triton paper also, that for sure is atmosphere.
Yes.
So, yeah.
Mathematics.
So this one was the best resolution one,
Mhm.
and was hard to see something exactly possibility of being quality. And another one has also little resolution, sometimes that and it's always like
Above.
yeah, above. So no clear evidence like a shape or something like that.
Because there are some theories about local and seasonal atmospheres in large CNOs. So since MS4 in 2003 are large CNOs, they could be, you could like, this, yeah.
Yeah.
But I understand.
Yeah, I mean, it was so hard to get this data that I don't focus much. I look at everything, but I don't focus much in searching for other things. I was focusing on finish this creator thing and publish it. But now we can see again the data.
Take a look with other eyes.
Yeah,
for
fresh
other
eyes.
But is there a leaf like what when you said large CNOs, what are you? Like what size?
larger than 500 kilometers. They could have, it's the case of Iris, Mathematics.
And because in Magamaki we found an local atmosphere and then
Yeah.
with occultation.
Yes, so this is a theory, I guess, from in some of books from Leslie Young. She makes some counts about probabilities, how that looks like. And since Pluto occultations data has this very like atmospheric shape with present peak and everything, every time that was like the time that Alex published the data from 2003 AVA4, they were talking a lot about the possibility of looking for even most for mathematics as well, because mathematics is dominated by CH4. It's a very volatile material. So it can easily, when it's passing close to the perihelion, like evaporate a little bit and detect some gas, like local and temporary seasonal atmosphere. So
To detect it, we need a high resolution.
So let's build higher resolution. Let's get this.
Yeah, so can you go back to the light curve before I think to the light curves?
The AZ. This one?
Yeah, there. So what you're seeing in the ones in the bottom at the bottom, you see that there is something falling in the middle of the drop. That's because the exposure time is long enough to have like part of the occultation and part of no occultation. And that's why you have that point there, but it's due to the resolution. It's not because you have an atmosphere. When you have an atmosphere, you have to have more degraded, more
Okay.
like
Is good.
When you show this sort of square thing, I often wonder, I think it is related to what the question Emily has asked. You could have the diffraction pattern, the diffraction due to the edge effect. So you are saying that your sampling is dark enough such that the diffraction pattern gets washed out? Is that what you said?
Usually, yeah, usually. Because usually the refraction patterns affects, you know, slight curves, even though it's I don't know exactly if this one, but like this, they have a little bit big here, on the model, you can see it. But usually the exposure time is longer than what is. In some of few light curves so far, I saw some like that. Now that we are studying the power, the charity rings, so it's really high resolution, high frequency images. You can see a little bit the data becoming to have some personal patterns. But right now, that we are getting more data in less time, usually is not a problem.
Isn't it much more, if you take that, isn't it much more a stronger constraint on the shape of this? I could,
I mean, if we can detect it,
Yes.
I don't know. Then people know.
I mean, it's an impulse response thing, right? So you're right.
Yeah.
If you catch that, then you know that where the edge is.
Oh, so we can calculate the exact edge.
more than that shape,
Yeah.
I'm not the same person.
Yeah.
Good catch, yeah. You can think about it.
the other thing which may wash out is the atmosphere.
Sorry,
The atmospheric turbulence also may wash out that diffraction.
yeah, maybe, but as we use another stars, this comparison, we can use most of the atmosphere. I mean, these light curves,
Is it common between the two, the turbulence? The turbulence
yeah, because the
right?
because it's so small, then turbulence usually are centimeters, I think, large,
Yes.
right? So they are seeing a really, 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 really small part of the sky. So if there is turbulence here, probably they are affecting all the target star and another ones also. So usually we think that we remove most of the atmospheric turbulence from the data because we use.
My nice thinking is that if you want to do that, your second star should be within the characteristic length scale of the turbulence, which is only 2 seconds.
Okay.
Otherwise, the turbulence will be independent.
Mhm.
It will be independent, it will not be independent. That's why I think it is.
Okay.
Any other questions? So let's thank our speaker again.